So we know many things about light already. We know that it travels in straight lines near enough, and so it's either stuff, like particles, or else it's a very short wavelength wave. We know that it travels very fast, but at finite speeds. So it takes light about 8 minutes to go from the sun to the Earth, and just a small fraction of a second to go around the Earth. Or if you bounce up across a satellite and back, then it takes an appreciable fraction of a second, and you can notice it in a phone call. Light travels in a vacuum. It does in fact go from the sun to the Earth, and there's no stuff there for it to be oscillating in. So it's not a mechanical wave, it's something else. So it's either some special kind of wave that can actually travel in a vacuum, or else it's actual stuff that's being emitted by the sun. But our everyday experience of light doesn't depend so much on the details of what it is. It depends on more mundane things like how our eyes work, or how light interacts with things, how it reflects from things, and how it's absorbed. So our eyes are fairly amazing devices that convert light into electrical signals that our brains can interpret. They can do that differently for different kinds of light. We have some parts of our eyes that just tell us about the intensity of the light. And some parts of our eyes measure the intensity of particular colors of light. So loosely speaking, eyes have three kinds of color receptors. They have those that measure things that are kind of red, they have those that measure things that are kind of green, and those that measure things that are kind of blue. And if you have an equal measure of these things, then you can use those to figure out what the colors are of any particular thing you're looking at by seeing the different ways in which these different receptors are being affected by the light. And we also have some receptors that just measure the total intensity of the light of all the light. And those are more sensitive, and so though they can't tell color, they are good for things like night vision. And that's why you don't see color as well when it's very dark. So the detectors that are very sensitive to light but can't discriminate between different colors are called rods because that's what they look like, that's their shape. And the ones that are very good at detecting different kinds of color are called cones. For the same reason. They have the shape of a cone. So some people have extra kinds of cones in their eyes, and they're particularly good at detecting different color changes, particularly subtle ones. And some people have less kinds of cones in their eyes, and they have various forms of color blindness. So they can tell that there's light there, but they can't tell exactly which color it is. Now, what is this intensity that eyes are measuring? Well, you might be able to guess from the units. So intensity is measured in terms of watts per square meter. And so it's a certain amount of power per square meter. So if I imagine I have a light source, maybe it's a star or a candle, and it's giving out a certain amount of energy per second, and 1 joule per second is a watt. But that energy is going out in all directions. So if you've got a star sitting in space, the light that it's sending out goes out pretty much equally in all directions. And so the Earth doesn't receive all the power that the sun's putting out. In fact, it only receives a small fraction of it. If we have the sun here, and then we have the Earth going around it, not to scale, then the sun is putting out energy in absolutely all directions. And so what fraction of that total power output of the sun does the Earth in fact get? We can work it out by thinking of all of that energy being spread out in a sphere. So if you have a sphere around the sun at the radius of the Earth, then any piece of that that's sort of the Earth's size will get exactly the same amount of energy as the Earth. And so we've got that same amount of energy per second, that same amount of power going out in all directions. And if we want to figure out how much the Earth gets, we have to work out how much of that power is going out per square meter. And we can see that that is going to go down the further away we get because it's going to be spread out over a lot more square meters. Remember, the surface of a sphere goes as the radius squared. So the surface area scaling is the square of the radius. And what that means is that the amount of power per square meter is going down as the inverse square of the radius. So the intensity is defined as the power per unit area, and it tends to go down as the inverse square of the distance between the source and the receiver. One of the really impressive things about eyes is that they work very well with a very large dynamic range. What that means is that they work very well with very high light intensity. We can work in very bright areas and still see reasonably well. And we can also work in very dark areas and see surprisingly well.